Okay, in this video we're going to graph some pretty straightforward logarithmic functions, and the first one is y equals log base 2 of x. And of course what you have to keep in mind anytime you're dealing with logarithms is that the input, the x in this case, has to be positive. So that would mean we're going to start with some positive values, and probably the best one is that if you can set x equal to 1, you simply just have to evaluate this log, which is log base 2 of 1. Now remember, this is saying 2 to what power gives me exactly 1, and of course that is a power of 0. Remember, your logarithm is simply the exponent in exponential form. And the next sensible x value, of course, is to copy your base and rewrite that inside. So make your input 2 in this case. And that's a pretty trivial log to evaluate because this is saying 2 to what power gives me exactly 2. Of course, that is the power of 1. And the other x value I will probably prefer to use would just simply be the reciprocal of this base. And since the base is 2, we'll go with 1 over 2 or a half. And now we just have to evaluate log base 2 of 1/2, which is essentially saying, of course, that 2 to what power is the reciprocal of 2, and that is the power of -1. So once we plot these points, we'll get a pretty good picture of what our function looks like. So when x equals 1, this log outputs 0. When x equals 2, this logarithm outputs 1. And when we input a half, our log function here outputs a -1. So something else, of course, to include in your log function will be the fact that we have a vertical asymptote here. So it's kind of counterproductive maybe to include it here, but of course our y-axis is a pretty good visual. It'll allow us to see that that is our vertical asymptote, but we will still, I will put it here in color so we can see it. It's pretty thick, but anyway. So there's our vertical asymptote. So if I ask you for the equation of a vertical asymptote, you don't have to think too much in this case. It's just our y-axis, but just remember the more formal way of defining your y-axis is the x value at which it occurs, and of course that would be x equals 0. So our vertical asymptote, in this case, the equation of it is x equals 0, and very much related to that is the domain of this logarithmic function. And of course, the key piece is that x has to be greater than 0, and we can use the whole set builder notation if we like. Set of all x such that x is a real number, so that we're only inputting real numbers. And of course, the key piece there is that x has to be bigger than greater than 0. And please do not include the line in your inequality. We can't input 0 because that is undefined as well. Okay, so the last thing to do here is, I guess, bear with me as I try to connect the dots here on my tablet, but we'll see what we can do. Do it in baby steps here. And of course, once I get close to my vertical asymptote, I'm going to try to exaggerate the fact that this function will not cross that y-axis, will never make contact with its vertical asymptote. So this is the graph, of course, of y equals log base 2 of x. Okay, so the next logarithmic function we will graph is y equals log base 1/2 of x. I'm sure you can recognize that this base is reciprocal, the base in the previous example. But that doesn't change a whole lot in our process. If I can make my input on a log equal to 1, this is a trivial log to evaluate, just as it was in the previous example. So now I ask myself, 1/2 to what power is 1? Well, power of 0 is still the answer to that question. And then the next x value I will use is basically just recopying this base. It happens to be a fraction, but that's really no bother. As soon as you say to yourself, 1/2 to what power gives me exactly a 1/2, and of course that's just a power of 1. So notice, and no matter what logarithm you're dealing with, no matter how many transformations become present in future examples, you always keep this same approach to pick an x value so your whole input is 1, and also to pick an x value so that your input actually just basically copies your base down again. And then the last x value, of course, we will take the reciprocal of this base. We'll put in a +2, In this case, it's a very trivial log to evaluate once again. So half to what power gives me the reciprocal of a half? That is a power of -1. So we'll plot these 3 points. And note, we still have an x-intercept of 1 here, even though we changed the base. All logs without any transformations, all logs will have an x-intercept of 1. Our next x value here, I guess, is a half, and that goes up to +1. And then finally 2 and -1. So I'm sure you can see that this is an upside down version of the previous example, which means it has exactly the same vertical asymptote. If I can get it on the screen here. So of course the y-axis is pretty visible there, but I'll just put a colored version of our vertical asymptote right over that, just so you keep that in mind. If at some point our logarithm does get translated away from that y-axis, which I'm sure we'll deal with soon. Okay, so we still have a vertical asymptote. It's the y-axis, so I guess we'll copy that down as well, the equation of our vertical asymptote, even though that hasn't changed. So the equation of that vertical asymptote, the y-axis, or x equals 0. And once again, our domain hasn't changed here either. So we'll copy down this set builder notation again. So the domain is the set of all x's such that x's are real numbers. So x must belong to the set of real numbers. And of course, the key, the punchline, is that x must be positive. We do not want 0 or any negatives in the input of a logarithm, because that is will output a number that's not a real number, and of course won't be visible on our graph. So the last thing for me to do here is attempt to connect these dots, which, believe it or not, is a little painful on the tablet, but I think I complained about that already. I'll try not to complain about that every single example. Okay, so it's a little wavy. I think I'll do the baby step approach again. Okay, so it's a little rough and a little scratchy, but I think we can see that, yeah, okay, that looks like it's an upside down version of the previous log. So I guess I'll record the equation here on the graph. So remember, this is y equals log base 1/2 of x. And just so we can make a better comparison, of course you can rewind the video, but I'm going to actually graph the previous logarithm again. Remember, of course, it still had an x value of x-intercept of 1. And I think you can check back. When we had a half, it was -1. And when we had 2, inputted 2, we got a +1. So, of course, this is the previous example. And I think you can notice here as well. Find this a little easier to sketch, going in this direction. I think you can also notice that, of course, this is y equals log base 2 of x, and that seems to be a reflected version of the function we graphed in example number 2 here. So that would mean if we reflect log base 2 of x across the x-axis, apparently it's mathematically equivalent to log base 1/2 of x, and that is a little bit confusing. Let's just make sure we record it up here. That would mean if I take base 2 log of x, put a minus in front, I will reflect it across the x-axis, and all those dots will our order pairs will coincide with the order pairs we got when we graph log base 1/2 of x. So let's try to demystify that a little bit by just kind of analyzing the equation that we're dealing with in this example. And I'll rewrite it here in a moment. I'll do a pen switch here. So we're dealing in this example with log base 1/2 of x. I want to somehow show that that is the same thing as reflecting log base 2 of x across the x-axis with the negative out in front. Well, as always, when you're trying to make sense out of logs, first step should probably be switch to exponential form. So our base here is a 1/2. The log is the exponent, so that would mean this base raised to y would give us x, and that's the exponential form of this logarithm. And then as soon as it's in exponential form, you can probably notice that, hey, I can write 1/2 as 2 to the -1 and work with my exponent properties. Notice if I have a power raised to another power, of course that is the same thing as now 2 to the power of negative 1 times y, or negative y, equals x. And now we can switch back to logarithmic form. This would be this exponent minus y is equal to a logarithm of base 2 of x. And we'll divide both sides by negative 1, or just change the signs on both sides of this equation, and now we can see that that is definitely mathematically equivalent to minus log base 2 of x. So you'll find in many of the examples in the practice problems, I don't bother with base halves or positive fractions. I usually just put a minus out in front and deal with the reciprocal version of that base. And to further demystify this, and I think you can remember back to your in exponential functions that if we had y equals 2 to the x versus y equals half to the x, remember that these things were actually just reflections of each other, and of course that's across the y-axis when dealing with exponential functions. So it should make sense that if we switch our bases and logs, we get a reflection as well. But of course, this reflection is, I guess in pink here, going to be across the other axis. Since remember, we're switching x and y completely. So these two logs, when they swap bases, are reflections across the x axis. Okay, in our last example in this video, we have a logarithmic function chock full of transformations. So I guess don't panic. We're still going to try to duplicate the process that we saw in the first two examples. And also to reinforce a key concept of this video, you note that if you have a log base 1/3, that we can switch that to a log base 3 as long as we remember to put a reflection out in front. And doing that, that will actually give us a little bit easier time of it, because that reflection will cancel the reflection in this given equation here. So to show you what I mean by that, we'll come down here, and instead of dealing with this logarithm, I'm going to switch that into a base 3 logarithm. Of course, we have to keep all of those other transformations, at least for the time being. So inside these square brackets, we'll put a logarithm that's mathematically equivalent to this one. And which logarithm is mathematically equivalent to this one? Of course, we will switch that to log base 3 of x plus 4. Note we have to still keep the same input, because both of these logs would have to be translated 4 units to the left. And don't forget, we also need a minus out in front. So if you're going to switch your base from 1/3 to 3, don't forget to put a negative out in front. Now, incidentally, you could use your change of base formula here. Maybe that's a little bit easier. You don't have to memorize this little trick of the trade. That if you want to switch to, and maybe we'll include that, it won't take long. If we want to switch from base 3rd into base 3, of course, we're going to have to stack a couple of logs on top of each other using the change of base formula, going to the base that we prefer here, an integer instead of a fraction. And note the old, and I'm ignoring the -2's for now. I'm still just focusing on the log. So remember, the old input argument goes on the top, and the old base goes on the bottom. And I think you can see that at the bottom here, 3 to what power is the reciprocal of 3? That's just a -1. So of course you take that -1 and write it out in front. So either way, change of base formula, or just memorizing this little trick that if you switch to from a 1/3 to a 3, don't forget to put another reflection out in front as well. Okay, and why would we do that here? Well, now of course we can multiply that -2 through in the front to this negative that's inside here, and of course that's going to simplify nicely and give us an equivalent logarithm that's going to be positive 2 multiplied by log base 3 of x plus 4 minus 2. Now you don't have to switch your bases, but just please be aware that it's definitely an option. And of course, that's what I'm going to use in this last part of the video, because I would rather, I think, deal with an integer 3 as my base, and then one less transformation to worry about is probably a good plan as well. But if you use the original equation, your graph will of course look the same as mine here. Okay, so I'll use this, I guess, simplified version. And now we have to pick our inputs a little more carefully, but maybe before we worry about that, let's just, I guess, say to ourselves, well, if I had this logarithm with the 2 at the front and the minus 2 at the end, but if I had log base 3 of 1, this would be a really easy expression to evaluate, because 3 to what power gives me 1? That power would be 0, just like the previous examples in this video, except now we got a couple of transformations to include here as well. But this log, if we have a 1 in the input, it's going to give us 0. 0 times 2 is 0. 0 minus 2, of course, is going to output a minus 2. So we got to eliminate that entire log from that expression, which is definitely worth the hassle. And the only other difference now is we just have to ask ourselves, what x value are we going to pick to secure that 1 on the inside? And I'm sure you can see this by inspection, but if you don't, say to yourself, how would I make x plus 4 equal to 1? And you can subtract 4 from both sides and of course get minus 3. But I think inspection, just looking here and plopping in a minus 3, I think it's pretty easy to see that that is going to give you 1, the input of that log, which makes this whole expression super easy to deal with. So there's one ordered pair. You really only need 2, but I think we'll do 3 just for the practice. So the next one, of course, remember the other easy situation we saw in the previous examples is that if we can get our base duplicated in the input, this is a super easy log to evaluate, and of course this whole expression becomes pretty trivial as well. So log base 3 of 3 is 1, so this is just 2 times 1 minus 2. Which is 2 minus 2, or 0. And then if you can just look at this through inspection and say, well, if I put a negative 1 in there as an x value, I get negative 1 plus 4, which is 3. Of course, that's pretty efficient. If you're stuck, say to yourself, x plus 4 needs to be 3, so we have an easy log to evaluate. And of course, you'd subtract 4 from both sides and figure out that you need a negative 1x value. So that's obviously 2 ordered pairs. That's more than enough, but just for the practice, as I said, I think we'll do one more. If we can get our reciprocal, I guess in the correct color here, if we could get our reciprocal inside this log, I'm not sure if this is worth the trouble, this last ordered pair, but we'll include it for the practice, as I said. So if I could get a third in there, well then of course that's log base 3 of a third. So I need a negative 1 exponent to make sure 3 becomes the reciprocal of 3. So this whole log is equal to negative 1. So this expression is going to be negative 1 times 2 minus 2, which of course is minus 4. So I'll get rid of the scrap work here. So I guess the question is though, what x value do we need to pick to get a third in there? I think you can probably figure out that if I put some kind of a minus 3 in here, we can make sure this thing is roughly 1. And with inspection, you can probably figure out that it is negative 3 2/3. But if you don't see that, I better get a little more space for this last one. If you don't see that, of course, as always, take your input and say, how would I make x plus 4 equal to the reciprocal of 3, 1/3? Well, you'd subtract 4 from both sides. And then realize you got a fraction, so you're going to need a common denominator of 3. So you'd convert your 4 into 12 over 3. And I'll just keep going this way. So this is going to be now 1 minus 12, which is negative 11, over 3. And ignoring the negative for the time being, but definitely not forgetting about it. You can divide the 3 into 11 3 times. That's 9. It's a remainder of 2. So that's going to be the same thing as 3, a negative 2/3. And yes, of course, with that negative out in front as well. So we need to input 3 I should say negative 3 2/3, and by putting that in, I guess I should look here, putting negative 3 2/3 there leaves us with simply just a 1/3 left over in our input, and then we can figure out that log easily and get a minus 2 times subtract 2, which of course gives me a minus 4. So let's plot those ordered pairs, all three of them, and remember, you don't need 3. It might not have been worth the hassle to get that last one, but at least it's there in case you need it in a practice problem. So now we'll just plot these 3 ordered pairs. The first one, minus 3 and minus 2. Then we'll have minus 1 and 0. And then that actually might come in handy if we have negative 3 2/3, we're way down to minus 4. So I'll say 2/3 is roughly there. So this is the shape of our logarithm. Now again, keep in mind, I'm going to have my eyes right here, different color, to say if I'm dealing with this log, that's a base 3 that's been stretched. So of course this should take this contour here. And of course one other feature that you should include, not just because it's helpful, but it's an important feature of any logarithmic function, is our vertical asymptote. So we can see that this was a log that was translated 4 units to the left. So of course we'll include a vertical asymptote at negative 4. So we'll put that in as a solid line, and we'll notch that out. And there's our vertical asymptote. And even though, of course, we don't need it, I think I'll also just write down the equation of that asymptote and the domain here as we wrap up this video as well. Okay, so once again, I'll try to do my scratchy kind of connecting these dots. And I'm sure yours will be better on pencil and paper. Now, I don't know my y-intercept, and I'm not going to really worry about it, so I think I'll just quit while I'm ahead and don't stray too far from the 3 ordered pairs you can be confident about. And of course, this is the graph of minus 2 times log of base 1/3, x plus 4 minus 2, or equivalently, 2 times log base 3 of x plus 2 minus 2. So let's quickly identify the equation here of our vertical asymptote with a slightly thicker pen. So the equation of our vertical asymptote is going to be the location of your, I guess the x location of your vertical asymptote, which of course is at minus 4, and the domain, which I'm sure you don't have to label. You can, as the domain, as soon as we start seeing set builder notation with x's, I think it's pretty obvious we have to be dealing with our domain. So set of all x's such that we're only inputting reals, with the intention of only outputting real numbers as well, but let's focus on our domain. And of course the key part here, as you can see from your graph below, this x has to be bigger than minus 4 to stay in the area of our graph here, not to the left of our vertical asymptote, but in this case to the right of it.